Okay, so let's welcome our speaker.
Okay, thank you. Yeah, we lost many people here from the first talk. I'm from the famous neighbor, Peking University. I want to express my gratitude to the organizer and also particularly to Professor Yao for this kind of invitation. I have this opportunity to speak to you our efforts in last over 10 years to developing high-dimensional numeric methods. Okay, so why we need such high-dimensional numeric methods? We have a lot of different reasons or motivations for this, but for me, the motivation is if we want to cross this forbidden region or this boundary between classical world and the classical world and the quantum world, we actually need some very high dimensional mathematical model to do this. The big reason here is the classical world. For this one, this is the famous Newton, and we usually use the phase space. For example, use the position and the velocity, momentum to represent your object, your under consideration. So, but for the quantum mechanics mathematical model, you read textbooks, we use the wave function, the Schrödinger equation. And in Schrödinger equation, we not exactly or obvious explicitly use the phase space. So this is the big reason. In this part, we use the phase space coordinate, but in this part, we introduce the so-called the configuration space. That means the position plus time. So if you want to cross this boundary or this forbidden region, say a famous scientist, say Bohr, said maybe you need to use some amplifier to make you can cross this boundary. So if we want to do that, we actually need the phase space in quantum mechanics for describing this quantum world in phase space. So the reason is why we need to cross this boundary, right? You can sit very safely in this part or in this part. We don't need to cross this boundary. I think the big challenge here, or the big reason is we want to understand how human brains work. So for me, this motivation is we actually want to fill in this gap, this missing gap proposed by Roger Penrose. If we want to understand how human brain works, we actually need to understanding or make a more mathematical model with physical details to let you can go through this boundary. Otherwise maybe it's no hope. We can develop lots of AI tools, but we cannot understand why it works. So this is a big problem. And for me, this is our motivation to developing high-dimensional numeric methods. So where is the high dimension comes from? The phase space. So the mathematical model for quantum mechanics in phase space is called the Wigner function approach. Say this guy, right? It's my convention that we usually use this wave vector to represent the velocity, but it's the same, right? Just some constants for given objects. So the Wigner function, the Wigner introduced this objective function to represent all quantum information for the same system where Schrödinger does. That means this rho is the famous density operator. You can write it into the wave function, this diagram per psi. So this is a rho this density operator. But in order to obtain this wave function, you first need this coordinate transformation. That's you let your object move slightly a distance, and you want to see the effect of the reflection or effect of this object in velocity space. So we need a Fourier transform. Okay, plus these two together, we get this Wigner function. And after giving this definition, and you can work in details or derive this Wigner function or Wigner equation from the Schrödinger equation in a direct manner, just a step by step, and just use some property of Fourier transform, and you can get the working equation in this form. It is very different from Schrödinger equation because you will see this f is a real function. And you can interpret as a distribution, but it's not a distribution because this f can take negative values. But you can use it like a discrete function. That means you can calculate some average, just like a discrete function. And then, this is the first difference. And the difference. The second is this equation, right? You can see it's a non-local model and show a naturally first derivative system in time and in position. And also, but in momentum space or in wave vector coordinate, it's a natural non-local operator. You can see here this CO2 differential operator or this integral operator. See, and the V and this external potential can show this like a finite difference, central finite difference. Okay, so in the whole space, this Wigner function is totally equivalent to Schrödinger equation. But when you're working in boundary domain, you need very carefully including the boundary condition to make these two model equivalence. So, and this is and another thing is we can see directly inform that from this Wigner equation you can get back to the classical part. Say if you express this external potential with Taylor expansion and at x, and use some property of the Fourier transform, you will get this the following more expansion, and you can see exactly that this reduced Planck constant reflecting the quantum information goes to 0, right? When you go 0, the remaining part is so-called a classical Liouville equation. That means the Boltzmann equation without scattering, without classical scattering. So this is why we choose this Wigner equation, because it actually can let you go through from this quantum part to classical part. And it is the only one at the current stage we can do this. So say, in a word, say, in this part, in this quantum world, we have Wigner. In this classical part, we have Boltzmann. And these two equations can make a corresponding one-to-one each other, right? And also we can see that the Wigner equation have lots of applications in nano device, in semiconductor region, right? And you also in some hot density matter, and you can also find some very useful implications in quantum tomography. I want to say some words about this quantum tomography because we can see from this equation, you can from this picture, you can see that when actually this is analytical Wigner function without any new numerical effect. You can see very clearly that between these two parts, right, two branches, we have some oscillating structure between them, and this oscillating structure directly relates to how much quantum information is stored in this state. If it is no this oscillating part, you can say we have no any quantum information in this state. So this is the Wigner function approach, the biggest advantage over the classical over the common used Schrödinger equation. So that means we can exactly to show how much quantum information is stored in your state, in your quantum state. And also we can do some some applications in chip design. For example, you can this high dimensional nanowire. This is some example in hot density matter. The key thing is the key point is we want to fully use the correspondence between the Wigner equation and the Boltzmann equation because they show very similarity in mathematical formulation. So you can put them together. This movie shows you that when we integrate the Wigner equation by some advanced numerical schemes, you can see exactly the quantum double slit interference. See, if you put a plate here, you can see some dark bright interference phenomena here, right? And this shows you that you can get everything you want. What you have got in shading a picture, that you use Wigner equation function, you can also see the same thing. So my talk focuses on the numeric methods to solve this kind of equation. And we just set an example to develop high-dimensional numeric methods. Prior to this work, we actually have some efforts in the literature to solve the Wigner equation because it's so important. And you can divide it then into two aspects. One is grid-based methods. This is the traditional numerical schemes like finite difference, spectral method, or place spreading Wigner discrete clustering. But all these grid-based methods are restricted to no more than 4-dimensional phase space. Because when you want to describe your system in phase space, you actually need position and the velocity. It's a naturally high dimension, right? So also in the literature, we have another direction to integrate this Wigner equation. It's called particle-based methods. It's usually referred to stochastic algorithm. Say we have affinity method, sine particle, sine Monte Carlo, random growth, and sine particle Monte Carlo. In our work, we use some branching random walk algorithm to we develop some branching random walk algorithm to solve the Wigner equation. So the biggest challenge to integrate this equation is a high dimensional challenge, right? So it's called a curse or dimensionality. You can see a very simple calculations that we want to some xk, right? If n is one body system, you have 6-dimensional space, phase space. So in my talk, I want to show two typical examples in both grid-based methods, also in particle-based methods. The first part, we want to show some efforts in this one, in the first grid-based methods, and we actually work in this direction over 10. I think it's about 15 years. So the first part, we come to the grid-based. It's a very traditional one. It's a deterministic method. Say we want to solve this electron photon coupling system. That means we fix the nuclei, and we want to see the dynamics of electron. And this is a very classical quantum system. But when you put it in the phase space, you actually have a 6-dimensional equation to solve, right? You can see here, right? But when you solve this equation when you want to see the same systems in shading a picture, you must be very careful to deal with this singularity induced by Coulomb interaction. But in the Wigner function approach, this singularity can be easily moved to this part, this weak singularity part in the kernel of a pseudo differential operator. this is another advantage to use this Wigner function because it's naturally a non-local operator. So, but the remaining thing is how to, if we want to stick to the grid-based methods, how to store with the largest grid of this size. And also, you need to deal with this non-locality because this is a weak singularity, and also the nominated part is a high oscillating part. So that means if you cannot capture this high oscillating in enough accuracy, you may lose some. You cannot make very long simulations. And also another thing is singularity, oscillating, and non-local. But the biggest problem is the first one. It comes from the high dimensionality, right? So we want to stick to use the grid method to integrate this six-dimensional system. So how can we put it in an ordinary accessible high performance computer? We actually need to think about or develop techniques in at least in these three aspects. First one is we actually need a step time integrator because when you use HPC, you usually need to stay in line to apply your computer your resource to make your computation fast, right? So when each time you get the chance to calculate, you need to output some results. So we actually need the time integrator must be stable. If you get some NAN, it's not work. You waste your money in this high HPC. Another thing is we need to design some accurate and efficient algorithm to approximate this non-local operator because singularity, oscillating part also both show in this term. So we must be very careful in this part. The third part is when you talk about using HPC, you use developing some load balance algorithm is the key. So we need to use some distributed computing to finish this task. So after some tests and attempts, it turned out to be that this three choice corresponding to these three parts can be work, but maybe not the best one. For the first, we transfer to we have request to this called the loss integrator. I think it is the order of this integrator close to between 1 and 2. And the key part is in this integrator that it fully respects to the first derivative system. That means it fully keeps the structure of the characteristic line structure. So it must be more stable and does not show very strict restriction from the CFR condition. So this is the first one. The second one, we use some truncated kernel method to deal with the pseudo differential operator because we need to care about the singularity, the high oscillating part. So we use some. This is close to the spectral method, very close to the spectral method. And for the X space, for the X and T space, for the X space, we first choose some finite difference, but later found that it's not so good. So we transfer to this local spline method, and it's very common in the Boltzmann equation community. So when we put these three together to solve the Wigner equation, and also we developed some mixed precision technologies because we we use a double precision in wave vector space and use a single precision in X and T space. This technique can reduce the memory requirement. Okay, so this slide shows you the Lawson scheme because you can see we write this kind of this is a linear part. This is a this is local linear part. This is a non-local part. So we fully respect this local part. That means because the local part is first delivery system, so they have some characteristic line structure. So we integrate we integrate this we fully respect this part and then use some approximation in this non-local part. So we get this predicted characteristic system. It's called the Lawson scheme, and we found that it is more stable in long-time evolution, and there's no any operator spreading error, and also the same numerical phenomena also observed in the Boltzmann community. So this is for the first part. The second one, this slide just show you if you use the operator spreading, you can see some unstable phenomena. But use Lawson is very stable until the final time is 20 atomic unit. And also, for XT space, in X space we use the locus prime, right? The locus prime, and we use the cubic prime, and we found that it can strike a acceptable balance between accuracy and efficiency. It induces low numeric dissipation, and the more important part here is the expansion coefficients can be solved efficiently by sweeping method. That means it can be easily distributed in high HPC. You can see here, right? Because the linear system to determine the coefficients have show some this exponential decaying structure. For example, we only need to keep the elements of the linear system around this diagonal part. When it goes from this diagonal part, it decays very fast exponentially. So we can truncate this off-diagonal elements and make that means you need very low communications to inverse this linear system. Okay, the same, right? This is the same details. I want to mention that. So the last one is how to accurately calculate this pseudo differential term. We use this so-called truncated kernel method. That means we first truncated this entire space. As I also mentioned that the Wigner function it's equivalent to the Schrödinger function requires some condition that this equivalence only works in the whole space. So when you put in bounded domain, you very carefully about how to choose the size of the bounded domain. So you need a large enough to make sure these two mathematical model equivalent. You can find some more details in this reference to see how this truncated kernel method working for this non-local operator. So we put this convergence curves show you that we actually can get the machine precision for non-local operator. That means we actually capture the singularity plus the oscillating show in this kernel part. So this is why, because this non-local operator or this non-local term contains all quantum information. if you lose some accuracy in capture this one, the result, the numerical outcome of your code is not so reliable, even especially in long-time simulations. So we called this the resulting algorithm the CHASM. This characteristic activation spectral method, and we found that it works very well. See, works very well. This is just a benchmark test for this one as state, and we can see the expected accuracy convergence. So they show you the dynamics of the electron under fixed nuclei. When you project the Wigner function into momentum and X space, you can see a very nice uncertainty phenomenon. This you can see this is a negative part, right? This is a positive part, and the physicists believe that this kind of structure represents the uncertainty principle. You can also make this hydrogen this H2 plus system. That means you have two nuclei fixed and one electron under the dynamics of one electron under this two nucleus attraction, and you can also simulate it, and you can see the algorithm keep this symmetric structure very well. But I want to say the price we got this movie. You see, we actually simulate this system in, I think we use 400 cores. 400 cores, but it takes over 20 days to get this movie. So you can calculate the price. We also test the speed up ratio. Use this kind of system. You can see we can get very nice speed up ratio. Otherwise, you cannot do the long time simulations if this ratio is not so good. So this is my first part, and you can see we can actually use this new technologies developed by computer science. The better computers, you will get the better results. And the numerical scheme, you can find all this numerical scheme in the literature. There's no any more new ideas. You just put everything together, find the very suitable one, and put it together, and use a large machine. You can do that things. So how about or why we need particle-based stochastic method? Say you because for the first part we fix a nuclei, but if you want to let, sometimes you actually need to let the nuclei is also like a moving part, right? It is free. So when the nuclei is also can move in quantum behavior or in quantum motion, how can describe this one in phase space? Actually, we have this 12-dimensional phase space plus 1-dimensional time direction. And if we can do that, we can simulate the hydrogen atom in truly first principle quantum simulator, right? We do not use any RT techniques to say to remove the singularity, or no such things. So we actually use this. Still, this is the original Coulomb system, and so if we want to solve this 12-dimensional model, you will find that the current computers cannot finish this task if you want to use grid-based methods. Because for the last part, we use mixed precision technologies. You also need over one very huge memory size, right? But for this 12-dimensional, it cannot work. So so another direction that we many experts realized this issue a long time ago, and we have and it has been developed very famous several kinds of stochastic method to solve this Wigner equation. But as far as we know that all of these simulations are also restricted to 4-dimensional phase space. If we want to go further to high dimensional, it also some you will meet some challenges inside hide it in your schemes. So I want to say a word about stochastic method for integrating deterministic PDE. Usually, for students working on numeric method or numeric PDE, people cannot put lots of put lot aside see stochastic method. But we want to say that I want to point that even in the first the famous CFL paper published in 1928, it also mentioned a very dedicated stochastic method to integrate this wave equation. Say this if you use central difference plus the first order system to integrate this thing, and you get this one, and you can integrate this one half as a probability. This is a very famous random walk algorithm in the paper 100 years ago. So the biggest meaning is it connects the stochastic analysis and the deterministic PDE. So so for our system, right, for our Wigner equation that is non-local part, is non-local integral equation that how can we do the same things? I think the biggest challenge also comes from the pseudo differential operator, because the kernel can be negative, and also some singularity and also rating. So you can, if you, this is a very abstract form that if you want to inverse this one, and you can use the Newman series expansion, that you will get this one, right? And this the first order, the second order can give you this is no jump, right? This is a jump once, jump twice, but when you write, it cannot be directly applied to the Wigner equation, because the kernel part, the kernel in this one, in this problem is non-negative, right? But for Wigner, we have the kernel can be negative. So we used some very direct manner to deal with this one. Is just use this we keep this positive one and put this this minus 2 into this minus sign into the weight part. So that means you will have a jump once, but this negative will goes to the weight of the particle. So that it will also bring some another thing, that you will have to introduce some branching mechanism. So use this abstract idea into the Wigner function. You can get, okay, for obtaining this formulation, we fully used the linearity of the Wigner equation, and you will see that, right? This is the zero order part. It's frozen. It cannot move, and you will get the negative sign into the weight, right? The weight, and this is the Poisson distribution to give the life of the particle. And this is gives the transition kernel. And when you take out the negative part, you will get the positive transition kernel. So that means you only use the random walk. It's not enough to simulate this Wigner equation, because the Wigner function is not a real, true distribution function. So you need to introduce some mechanism to representing the negative part. So that means this is why we use the so-called sign Monte Carlo method. Sign. So you see, this just shows the rough idea in the simulation. This deterministic movie comes from the first part, comes from the CHASM. This reference movie is very is reliable, and if we want to use particle method or stochastic particle method to represent this dynamics, we actually induce the red particle to representing the positive value of the function, and the blue particle to representing the negative particle values. And you can see, and also because this non-local part has more than one terms. How many terms will have some? Will give you how many particles? So you must have some branching mechanism to do that. You can see if the red particle or blue particle can be created randomly, and it also move according to the solution behavior, right? You can see very clearly that. Okay, we prove that this such a branching random walk algorithm can capture the Wigner function without any numerical errors. It is actually the same. That means the first moment is nothing but the Wigner equation, and the error comes from the variance, and the variance will exponentially grow with the time. So this exponential growth in time is also referred to the numeric sign problem in stochastic algorithm. So how to deal with this numeric sign problem? We actually found that this is a very fundamental mathematical problem. If you want to use probability method to approximate a general function, because when you use a probability method to approximate function, that you usually imply the function must be positive. No negative values can be allowed in the distribution. So when you want to approximate this f with probability method, that means you actually need this sign empirical method. Say this we have P, capital P, refers to the positive part, the number of positive particles, the red one, and M is the particle numbers of the blue ones. So when in response to this this exponential increase with time, the particles number P, capital P and capital M, will also increase exponentially. So when these two numbers exponential close, in a very short time, you cannot make these simulations goes on, because the memory size will be override over, right? So we need to develop some mechanism to destroy the particles, but without lose accuracy. So the problem is the problem is before we get to the discrete or discretized level, we first want to see in the continuous level what we can do. So we first introduce some standard valence reduction techniques to cause stationary phase approximation. That means you can see right here, right? We divide the integral from the frequency coordinate, low frequency and high frequency, right? Because it is a Fourier transform, right? So the high frequency part can be well approximated by stationary phase approximation. The low frequency part, you still keep the same formalism, right? So in asymptotic manner, we can get this approximation, right? It means you in the continuous level, you can also get some efficiency benefit without losing accuracy. You just need to choose carefully this lambda 0. I think the big point here is when you want to use stochastic method to integrate some systems, you usually the accuracy can be systematically improved, but you cannot expect very high accuracy because the Monte Carlo sampling gives you 1 over square, right? The minus square order. So this slide shows you SPA, this stationary phase approximation in approximating this integral operator, and you can see it actually works in asymptotic manner. But even for the low frequency part, the numeric sign problem is still there. You cannot get rid of this numeric sign problem. So the problem, the mathematical problem turns out to be this one. You have a sign empirical merger, right? And you want to get another sign empirical merger. But the number size, both in positive part and in negative part, you removed or destroyed this Na particles. And you want to see this nu and this mu and this nu still keeps the accuracy for a given test function. This is the first. This is the rigorous description of numeric sign problem. If you can find some way to keep this error, and at the same time we have very efficient scheme numerical algorithm to keep this error, then we can solve the numeric sign problem. So it's very delicate mathematical problem, and we found a way. I think the idea behind the following method is very straightforward. Say, okay, this example show you because when you two samples in this distribution, this negative part, the positive part, we will find lots of particles inside between them. But if you allow, they can be destroyed. You can see this one, right? So you remove or destroy the many particles between this region, but the accuracy is the same. This picture, the particles with larger numbers, and with this picture with less numbers, also approximate the same distribution. And with this picture show you that you can use more or less particles to approach this one, and if you can do everything correctly, right? So usually people use histogram. They say you use many uniform cells, and you calculating in the numbers, the positive one and negative one in each cells, and allow them to be destroyed. And but this the histogram is still restricted by the dimension, the high dimension, right? You need use the uniform cells. So it, according to our experience, it usually works in less than 6-dimensional problems. And also, it's the weakness of this histogram also mentioned in this paper to solving the Boltzmann equation with a stochastic particle method. So we propose a method to find a way to solve this problem or in feasible way, because it's called SPADE. SPADE. It's a sequential clustering particle annihilation through a discrepancy estimation. That means we first divide it into all the particles into groups. In each group, the particle share the same distribution, but the distribution is very close to a uniform distribution. So describe this uniform distribution, the distance between this particle distribution with the underlying the uniform distribution is this star discrepancy, right? This is a particle distribution, right? This is underlying uniform distribution in the same region. So the distance between them is star discrepancy. And it's very it's used in quantum Monte Carlo, the quantum Monte Carlo region. So, but if you want to calculate this dn star, it's NP hard problem. But we can have some approximate algorithm to find we found the local optimum. I think it's local optimum that works for our SPADE algorithm because we only need the value of this star discrepancy is less than some bounded, and with this bounded, we can prove the whole the SPADE, the accurate SPADE is in accordance with Monte Carlo error. So the key idea behind this SPADE is we introduce some adaptive clustering of the particles, right? And we get rid of the uniform cell division in histograms. See, this same picture show you, right? You divided these particles, and you will find that the region, this cell is not uniform, and in each cell, we control the star discrepancy is less than a given bonds, right? And then we destroyed the particles, negative, the red one and blue one, and we get this one. And the last particle distribution, the difference between this the first picture and the last picture, the error control, the error is can be controlled, and it's in accordance with the Monte Carlo error. This is the algorithm SPADE gives you. So you practice this idea into the branching random walk algorithm, because the particle can be correlated. So you need this SPADE, right? And you can see for 6-dimensional problems, right? You can see this is comes from the CHASM, the first algorithm in the first part, and this from the second stochastic algorithm. You can see, I think we put the price here, right? You can see there's the very similar, right? But you can see if we put in zoom in, zoom out, zoom in, you can see some difference, but it's very similar, right? And we can also calculate the error. It as expected, it can be the error between these two can be systematically improved by increasing the sample size or reducing the start discrepancy. So we actually solved the 12-dimensional quantum kinetic equation, this one. And we found that this is dynamics of the electron, and this dynamics the proton. And in short time, in a very short time, the electron's dynamics is very similar to that when the nuclei is fixed. So this similarity tells you that the Born-Oppenheimer approximation is reasonable in short time simulations for these quantum systems. But when the time goes longer, you will see a much more difference between these two dynamics. That means the quantum behavior, the quantum behavior of a nucleus actually takes over in some situations when the time is long enough, because the proton, when the time is long enough, the proton is not fixed the same place. It actually moves. Okay, so we put this reference just tell you that solving high dimension problems is actually very challenge, because for stochastic algorithm, the first two-dimensional stochastic algorithm appeared in, I think it's in 2003. And but if you want to directly extend this two-dimensional solver into four-dimensional, it doesn't work, because in the 2003 solvers, introduced many physical approximations. It can give you some curves, but maybe without the accuracy in mathematics. So if you do everything right, you can get this picture. Let's see. This blue lines is the reference one by deterministic method, and you can see this purple ones was generated by the 2003 solver. You can see, you can see some accordance where it's matched very well in some region, but in this region, that's not very matched very good. But when do everything right, you can because we prove that the first moment of this stochastic model is nothing but the Wigner function. So it must be in accordance in this way, right? So so we want to say that if you want to use grid-based method, if your problem is less than 6-dimensional, you can try. But when you want to go over or higher than this 6 dimensions, you only use these computers, maybe not very helpful. You must introduce some mathematical ideas, and our efforts in stochastic particle method to solve the equation is that the particles must be created, can be created, also can be destroyed. The master can be moved. Master can move according to your solution. Okay, so today the talks we are giving today is mainly comes from these two references. And the first author is my former PhD student, now is working at the Beijing Normal University. And also, the second paper works also with Professor Zhang Yun from Tianjin University. And you can find more details in these two papers. So the take-home message is, I repeat it again, that if you want to solve the problem in less than 6 dimensions, you can trust your computers. But you need to be very careful in choosing numerical scheme. But all these numerical schemes already appeared in the literature. But if you want to go higher than this dimension, the grid does not work. You need to use a particle. This particle means no grid, no mesh. And the particle is also another same sample. This particle is just a mathematical particle, not physics particle, right? So, when you want to use this particle-based method, the probability integration you cannot avoid. You must use this stochastic one. And for this direction, you need to introduce some new concept. This new concept, we actually need this new concept because we want to keep the accuracy. Otherwise, the numerical results may be not reliable. Okay, I'm finished. Thank you.
Hey, any questions? Yes, please.
May I ask a question? Is there any stochastic ways in computational quantum field theory?
Sorry? Is there any what?
I mean stochastic ways or method in computational quantum field theory.
I think the question is, we're talking about computational problems from quantum mechanics here. Are there any applications of the same ideas to computational quantum field theory?
Yeah, sure. I think it also have some try in CFD. Right?
So how to prove the convergence in quantum field theory?
Well, it's a good question. I think it depends on your problems. Because even in this Wigner equation, we fully we used many mathematical properties of this equation. It's not a general way. So we actually putting this stochastic particle method to another kind of equations. So it depends on your problem, I think.
Okay, thank you.
Other questions? Yeah.
Currently, I think we can work with over now. We actually finished the 12 dimension, right? Yes, and I think we can put forward on maybe I think 18. It can work. Depends on your problems, right? If you make a decision, you want to simulate some problems in over 12 and less than 20, I think we can try it. You can see, for example, you can see even for this 12 system, this is the price, right? Oh, sorry. This is the price. You can calculate the price. Yes, sure. We actually, you can see this is the arrow caps, right? Well, no. yeah, this is a big problem in high dimensional numerical simulations because we don't have the reference solution is not so easy to find. Yeah, this big problem because so this why so let's say the main part of this talk from the second one. The first one, the first one is, we can say that the first one, the CHASM, this numerical screen, just want to produce some reference solutions. Otherwise, we cannot do that. We cannot find these error caps. So we can do benchmark test only in 6 dimension, in less than 6 dimensional phase space. But in 12 in this I think in this 12 dimension simulations, we do not have any reference solutions. So we just say that in a short time, you just compare the dynamics of electron with when the nuclei is fixed, you can see some similarity. Okay, I think the result is good. It's reliable.
My question is it possible to theoretically prove that your method can overcome the curse of dimensionality?
No, no.
Do you think it is possible?
Well, no, I don't think it's possible because the deep mathematical question is the PMP problem, right? Even if we do not know any answer to PMP, we don't know answer to your question. Okay. Because the method, I think the SPADE, the key part of the SPADE is to transfer the curse of dimensionality into an NP hard problem.
Yes.
Yes.
Oh, thank you.
Okay, any other questions?
So could you interpret why the convergence order of the lossy method is between 1 and 2?
Well, no.
And is there any idea to improve the convergence order?
Well, it's yeah, you can actually improve that. Use more stages, right? But when you want to some high dimensional simulations, I think the second order or first order is good enough. The key issue here is that you can know the way to systematically improve your accuracy, not the order in itself. Wait, okay. You see, we only use the 2 stages, right? If you want to get a high order one, you can put more stages here, right? But you also need to pay some prices to do that. But for high dimensional simulations, you just make sure your scheme is convergent, not the high order itself. Okay.
Okay. Any other questions? Okay, if not, let's thank our speaker again.
Thank you. Thank you. So.